Hi everybody, my name is Cameron King and today we're going to be looking at organic reactions. So we're going to be covering alkenes, carboxylic acids, your alcohols as well as your esters, and how we're going to move between each one and how we're going to create each one. Okay, so let's start with the reactions of alkenes. So we learned from the previous lecture that alkenes are when there is a double bond between two of the carbons in a hydrocarbon skeleton. Okay. Now the words we're going to be looking at in this slide are functional group as well as homologous series. Okay, so the functional group is the group of atoms or the bond between carbons that will give a carbon molecule or a hydrocarbon its specific properties. Okay, so we can have different lengthed hydrocarbons that will all have a similar functional group, and this will put them into what we call a homologous series. Now, a homologous series is going to be a family of compounds with the same functional groups, and if they have the same functional groups, it means they're going to have the same properties. Okay. So we know that the pattern for an alkene is going to be CnH2n. Okay, nice and easy. And we call them unsaturated hydrocarbons. Okay, it's because they don't have the full number of hydrogens for the carbon skeleton. Okay, and when it comes to the combustion of these alkenes, it's going to be complete if it has enough oxygen. Okay, and this is going to give us CO2 plus H2O, just like the combustion of an alkane. Another reaction other than combustion that we can get with alkenes is going to be addition reactions. Now, addition reactions is when that double bond between two carbons is going to be broken, and instead of becoming an alkane, whatever breaks it is going to be substituted or inserted into that hydrocarbon chain. Okay, in this case we use XY. Okay, that just shows that it can be two different elements, okay, that are then going to be inserted into the hydrocarbon chain because of that broken double bond. Now you might ask, why would it do that? It's because those double bonds make it a bit weaker than if they were single bonds. Okay, they are unsaturated, and therefore there is the possibility of having that bond break and form two new bonds with new compounds. Okay, an example of this would be a reaction with the halogens. Okay, so we know from the previous lesson that to test for alkenes, we're going to use the bromine test. Okay, now bromine is a halogen. And what's going to happen is we know that that double bond is going to break, and it's going to take up those bromine atoms. Okay, so if we have something like propene being prop, meaning 3, okay, ene meaning an alkene bond, okay, propene plus bromine is going to give us dibromopropane. You see how it's now become an alkane because it's all single bonds between the carbons. Dibromo meaning 2 bromines. The same can be done for chlorine, fluorine, again any of the group 7 halogens. Okay, so as mentioned, these alkenes are going to be more reactive than the alkanes due to that double bond. Okay, so a simple reaction with hydrogen is going to saturate that hydrocarbon skeleton with hydrogens and therefore turn it from an alkene into an alkane. But notice that the number of carbons does not change. It is just that that double bond is breaking and therefore leaving it open to 2 more hydrogens saturating the molecule. We can also have a reaction with water in the presence of a catalyst and heat. So when an alkene is mixed with water in the presence of this heat and catalyst, we're going to get an alcohol. Okay, so what's going to happen is that OH group, well, firstly the double bond is going to be broken. Okay, now when it breaks, it's going to leave 2 spaces open. Okay, and those 2 spaces are going to be filled with the 1 hydrogen from H2O and an OH group, okay, from the H2O as well. Okay, now that OH group is what we're going to call the functional group. Before it was an alkene. Okay, so that double bond was the functional group giving it its reactive properties. But now it's going to be an alcohol functional group of OH. And that's going to give it a whole new set of properties. Okay, so alkenes plus water in the presence of heat and a catalyst are going to give us an alcohol. Okay, so as we said before, alcohols is going to be the homologous series. The OH is going to be the functional group. Okay, so here's some examples of the different types of alcohols we can get. And notice the wording and how we name these alcohols. Okay, methanol. Meth meaning one carbon. Okay, anol meaning it has an OH functional group. Ethanol, eth meaning two carbons. Okay, again with an OH functional group giving it that anol, ethanol. All the way to propanol, butanol, and so on and so forth. Okay, as long as that functional group of OH is going to be attached to the hydrocarbon skeleton, it's going to have an anol. Okay. The other examples that we're going to look at next are carboxylic acids as well as esters. Okay, so this is when they're not quite hydrocarbons per se, because they're going to have these non-carbon and hydrogen side groups, we can call it, the functional groups that will contain oxygen. Okay, so let's look at some of the uses of alcohols. So we know that alcohols can be used to make beverages, okay, alcoholic beverages. They can also be used in industrial processes, including the reacting of ethene with steam, okay, with a nickel catalyst, as well as alcohols which are strong dissolvents. So alcohols a lot of the time can be used as solvents to dissolve certain molecules. Okay, so some substances are going to be insoluble in water, but they might be soluble in an alcohol. Okay, we use ethanol quite a lot in the labs. Alcohol also has combustion, just like any other sort of hydrocarbon, okay, and it's going to produce carbon dioxide and water as well. Okay, what can also happen is we can mix it with sodium. Okay, so alcohols are going to react vigorously with sodium, and this makes sense because sodium is going to be highly reactive. Okay, and the sodium is going to dissolve to form sodium ethoxide. Okay. And another one which is going to lead us to our carboxylic acids now is the formation of a carboxylic acid where alcohol is going to be oxidized. Okay, oxidized meaning it's going to gain an oxygen in this case. I know in our previous lessons we talked about oxidation is loss of electrons, okay, which is true. Oxidation can also mean the gaining of oxygen. Okay, this can happen with something like rust. Okay, when iron rusts, it becomes iron oxide because it's going to have gained an oxygen. Okay. And yes, this is going to take us on to our next homologous series of carboxylic acid. Okay, so what exactly is a carboxylic acid? It's when instead of the carbon being saturated with a hydrogen, it's instead going to gain the functional group of COOH. Okay, now it's not as easy as just saying a carbon with an oxygen with a hydrogen. Okay, there's going to be a carbon with a double bonded oxygen and then a single bonded OH group. Okay, so as we can see here, let me just find my laser pointer. Okay, so this is our functional group. Okay, if we have something like methanoic acid, then yes, there is only one carbon. If we have ethanoic acid, then one of these carbons is going to have that double bonded oxygen and a single bonded OH group. Okay, but notice that that carbon is still going to have a full amount of bonds. Okay, it's still going to have 4 bonds, meaning it's going to have its full outer shell. Okay, and that goes all the way up depending on how many carbons are going to be in the molecule. Okay, so we're going to go up to butanoic acid with again 1, 2, 3, 4 carbons with a COOH functional group. Okay, so the homologous series is carboxylic acids while the functional group is COOH. Okay, then we're going to be looking at esters. the next homologous series. And what this simply is similar to carboxylic acids, but instead of that H at the end of the carboxylic acid, it's going to be replaced with another hydrocarbon. Okay, and this leads us to the naming of these esters. So it's going to be important to see that when we're talking about something like methyl ethanoate, okay, the methyl part is talking about the hydrocarbon that is attached to the single bonded oxygen. So the hydrocarbon that replaced that hydrogen of the functional group of carboxylic acid. Okay, that comes in the beginning of the word. So in this case it's methyl because it is only a single carbon. Okay, but in this case when we have ethyl ethanoate, okay, ethyl is referring to the two carbons attached to that oxygen where the hydrogen used to be. And then the next part of it, the ethanoate, for both of them I guess, is going to be the carbons that were originally a carboxylic acid. Okay, so how are we going to form these homologous series? So firstly, when it comes to a carboxylic acid, alcohol is going to be oxidized. Okay, it's going to gain an oxygen. And this makes sense because if you look at the carboxylic functional group COOH, okay, that carbon was always there. That OH group was also always there because we're talking about an alcohol. So the only difference between an alcohol and a carboxylic acid is that double bonded oxygen. Okay, and that comes from the oxygen that we exposed the alcohol to. Okay, it says in the presence of potassium dichromate. This makes sense because that acts as the catalyst. Okay, so carboxylic acids are weak acids as they do not fully dissociate or split up in water, okay, as much as something like hydrochloric acid does. And therefore it has a higher pH and lower concentration of hydrogen ions. So it's a bit more stable than your other acids, your stronger acids. Okay. When it comes to esters, the functional group is COO. Okay. And that's because it's going to then be attached to the other hydrocarbons, that other oxygen, remember. Okay. So how we're going to make an ester is by combining carboxylic acid and an alcohol. And what's going to come out is water and your ester. Okay, so ethanoic acid plus ethanol in the presence of an acid catalyst is going to give us the ester ethyl ethanoate, meaning there are two carbons on each side. Remember that the ethyl part is referring to the carbons that replace the hydrogen, okay, at the end of the original carboxylic acid. Okay, and it makes sense because that original carboxylic acid is going to lose a hydrogen, okay, and that original alcohol is going to lose its OH functional group. So that OH functional group and that lost hydrogen are going to come together to form the water that is given off by this reaction to form an ester. And yeah, esters are going to have very distinctive smells and are used in your perfumes and flavorings. If you guys take chemistry in university, they're going to have you make esters. I remember when I was in university, we made esters that smelled like paint thinners. We made esters that smelled like banana, okay? But I can guarantee you they do not taste like banana. Okay, so if you take any notes from this section, it's going to be this, okay? Here's a summary of how we get from an alkane all the way to an ester. So make sure you understand this, make sure you remember this, because it'll make these organic reactions a breeze for you. Okay, so we start out with our alkenes. Alkenes, two carbons that have a double bond between them. That double bond is highly reactive. So in the presence of water and steam, or water and heat, okay, it's going to then split up that water and it's going to become an alcohol. Okay, so that double bond is going to break. It's going to be replaced instead of by a hydrogen by the functional group OH, and it has now become an alcohol. Okay, alcohols are then going to be oxidized. Okay, and what's going to happen is in the presence of and potassium dichromate, we're going to form a carboxylic acid. Then to get from a carboxylic acid to an ester, we're going to be adding an alcohol, okay, in the presence of an acid catalyst to form our ester with the functional group COO. Okay, so the four homologous series that we looked at in this lesson: alkenes, alcohols, carboxylic acids, and esters. The functional groups that make these homologous series are going to be a double bonded carbons, OH for alcohols, COOH for carboxylic acids, as well as COO for esters. Okay, I hope you've understand this work. Please go over it again if you do not, and book a lesson if you would like to do some more examples one-on-one with this. We can look at multiple different types of esters. I know that can get a bit tricky when naming them. And best of luck for your studies. I'll see you in the next lesson.